Hello everybody, welcome to Unit 7. We're going to be talking about logarithmic functions and their properties and some applications of exponents and logs. I'm going to spend the first few slides here giving some introductory material and then also give a couple other videos where we go through some examples of using the logarithms, of solving logarithmic equations and exponential equations, and of some applications. So let's take a moment to review. What is a logarithm in the first place? And we ask the question, to what power must we raise the base a to get the result x? And the result of that was the logarithm. As an example of that, we said, well, okay, to what power must we raise a base like 5 to get a result like 125? And of course, we know that the answer is 3. But mathematically, if we were to take this information, put it in my Mathalator translator, and give the handle a crank, we're going to come up with a statement like log base 5, because we're taking that base 5 and we're raising it to some power to get 125. And the result of that, of course, is that we have to raise the base 5 to the power 3 to get 125. This is the logarithmic form of this statement. The exponential form, of course, would make perfect sense. We'd say, well, 125 is the result of raising the base 5, this small number right here, to the power 3. Okay, so this is our definition right here. That definition states the logarithm base a of x equals y implies that x is equal to a to the y. And this works both ways. Now, the problem with most people's calculators is that your calculator only really has two kinds of bases on them. If you use a typical Texas Instruments calculator, the only button that you'll see that says logarithm on it is the one that says LOG. What's implied is that this is a logarithm with a base 10. So we think, well, this means that we're going to be calculating something for a logarithm base 10 of some number. We call that a common logarithm, and the base is not typically indicated when we write the logarithm. The exponential statement that goes along with that is that x equals 10 to the power y. Likewise, most calculators have another button on them called ln. That is our other logarithm option with most calculators. And in this calculator, of course, the base is e. Now, we won't write a base e with our logarithm, but we do mean that we're trying to find a power to which, if we raise that base e, we would get the result x. And as we can see down here, we write this as ln of x, not log. ln, it means logarithmic natural. Ln of x is equal to y implies that x is equal to e to the y. This is our exponential form of that expression. Okay, so what do we do if we have something raised to a base that's not e or not 10? Well, in this case, we can use what's called a change of base theorem. The change of base theorem basically states that if we have a logarithm to a base that we don't want, like a, we can change it to a logarithm of the base that we do want, like b, and say, well, okay, the logarithm base a of x is the same thing as the logarithm base b of x, as long as we remember to divide by the logarithm base b of a. Now, this seems like a weird statement, but we have a way of evaluating in our calculator these buttons, and you should try this out yourself. Take a moment, and we can say, well, if we have a logarithm, no matter what the base a is, of some number x, then in your calculator you could use the common logarithm of x as long as you divided it by the common logarithm of a, and that's going to give us the correct answer. As an example, if I wanted to evaluate the logarithm base 2 of 7, the way I'm going to do it is I'm going to take the logarithm of 7, the common logarithm of 7, and divide it by the common logarithm of 2. Pause for a moment and try that out and see if you don't get out approximately 2.81. Likewise, if I don't like the base a, I could also change it to another base e. Take my natural logarithm of x over the natural logarithm of a. So if I was interested in, let's say, finding the logarithm base 4 of the number 0.4, it would be equivalent to taking the natural logarithm of 0.4 dividing by the natural logarithm of 4. And again, use your calculator, verify that this is the case. You should get 0.661. Okay, so just a little bit more notation for you right here so that you know it. Whenever we have a common logarithm, base 10, right, the base is 10, then we use this expression log of x. There's no base written. If we have a base that's e, where e, remember, is that natural number approximately 2.71828, and so on, a lot of other digits after that. If our base is e, then we write ln x. Now they also use some language here, something called an antilogarithm. What is an antilogarithm? Well, if x is equal to the logarithm of y, then y is equal to 10 to the x. So 10 to the x is the antilog for the common logarithm. And of course, if x equals ln y, then y equals e to the x is the natural antilogarithm. So it's the natural antilog of x. So when we say antilog, we just mean, well, the exponent. If we say antilog, we mean the exponent, 10 to the x. Okay, some examples to come.